Swayam Prabha. Digital India. Educated India.
So, welcome to the last lecture on stability of slopes. Today we will see a few case studies, and we will also look at the design of anchor trench for getting adequate capacity to hold reinforcement at the top of a slope. So, if a slope is coming out to be unstable, what is it that we can do to make it stable? So, we are using a very gentle slope of 3:1. Last time I showed you that even with a gentle slope of 3:1 you can have a little bit of problem. So, what all can we do? How do I make a slope stable? So, I can, simplest is I can make the slope flatter, right. So, to make cover slope or liner slope, reduce beta, reduce the slope inclination. So, we are now coming into that 3:5, 3:1 to 5:1, that is the preliminary slope that I gave you. Many landfills will have 4:1. What else can we do? Reduce W. So, just as an example, if I want to reduce W, what can I do? I have the W of the topsoil and I have the W of the drainage layer. Can I reduce the W of the topsoil by reducing the thickness? All depends on what you want to grow on the top, right. We said it depends on the root penetration zone. So, if you are going to grow shrubs or little higher than just grass, then definitely you need 45 centimeters there, if not 60 centimeters. So, you need 1.5 feet of soil. Can I reduce the drainage layer? Yes. How can I reduce the thickness of the drainage layer? Right. We can use a geocomposite, and let us say that if I have a 30 centimeter drainage layer, I can instead put a geocomposite instead of that. This will make a lot of difference to W, significant. Just if you were to calculate in terms of the weight per square meter, right. So, the gamma of the soil can be 2 tons per cubic meter, and this is 0.3 meters. So, it will become 0.6 tons per square meter. Instead, if I was to use a geocomposite, what would it weigh? Much lighter. What is the grams per square meter of the geotextile? I told you that you should adopt a geotextile of 400 GSM. 2 geotextiles, 400 plus 400, 800 GSM. Add the weight of the geonet to it, another 800. So, 1500 grams per square meter, that is 1.5 kilograms per square meter. And what was the kilograms of 30 centimeter of sand per square meter? It will be hundreds of kilograms. So, you can definitely reduce W by reducing thickness. The question is, can the geocomposite handle your water? Sand can definitely handle your water or sand gravel, but will the geocomposite handle it? If it does not, what will happen? Submergence ratio will go up. If submergence ratio goes up, factor of safety goes down. So yes, you should reduce W. What else should you do? Reduce submergence ratio if possible. What else can you do? Add T. That means add a reinforcing element. So all this can help you improve the factor of safety. Of course, without any doubt, try and increase delta. So in the case of sand, when I use a textured geomembrane, what is delta? 25 to 5, right? To increase delta, 25 to 5. Can I make my delta more than 5? I'll make my geomembrane really, really, really rough. Will delta become more than 5? No, it seems if it is smooth, it is less than 5. If it is adequately rough, it's equal to 5. If it is more than rough, will it become more than 5? No, because phi is the limiting value. No matter how rough I make my geomembrane, bigger than the sand particles, right? That looks very rough now. These are my sand particles. But what will happen when I make it very rough? The failure surface will pass through soil, and the limiting value will be, failure surface will not pass through this. It will pass through the soil, and therefore the limiting value will be phi. You cannot make anything rougher than the phi of the soil. The roughness can be larger, but the limiting value is phi. So I should increase delta. Problem is not with sand. You are able to get delta equal to phi with rough. Problem is the interface between the geomembrane and the clay. And in clay, the long term phi dash is anyways, depending on the plasticity of the clay, C dash is 0 and phi dash is definitely less than 25, if not 20. So you can at best take your deltas to 15 to 20. It would be too difficult. Somebody will say, sir, I'll put some sand in between the clay and the geomembrane. How's that for increasing deltas? That's a jolly good idea. When you move the geomembrane on the clay, it's giving low delta. So I'll put some sand. There will be no intimate contact, and therefore you'll get 0 out of 100 in an exam, and you'll get a lot of leakage in the field, and you'll be fired. Fired means if you are in America, you'll be thrown out. If you are a designer, it will be showcased everywhere how not to design a composite barrier, because the intimate contact is very, very important, and you will be decredited. That means you had a professional engineer certification, so you will say no, cross. So exactly this, don't put any sand between the geomembrane and the clay. Let's look at a couple of case histories. Real life problem. So what do you see here? Here the waste slope was not becoming stable. So what they did, whatever I have written on the board, they did not reduce the topsoil thickness, but they replaced the sand with a geocomposite, geotextile, geonet, geotextile, and they made the geomembrane rough. But now it is not about delta between sand and the geotextile, it is between the sand and the geomembrane, it is delta between the geomembrane and geocomposite, and the lower surface of the geocomposite is a geotextile. So this delta is geotextile to geomembrane. Agreed? That comes into play, and they have also put a geograde. So the idea was to how steep can we get this? W is down, delta is up, T is up. Looks like one of the best cover systems that we can get. Here are the results. How many cases? Dry, seepage, earthquake, earthquake plus seepage. You remember our acceptable factors of safety? 1.5, 1.3, 1.1 and 1.05 or something like that. So these are the three cases. And remember, I'm only showing you one table. I'm showing you a table. Oh, we forgot here a very important thing. What did we forget? I talked about height between berms, the height of the slope. So the lower it is, the better. Do remember that when I give too many berms, what am I doing? I'm actually flattening the slope. If I did not give a berm, the slope would be here. If I give too many berms, the slope is ending here. So I'm in de facto, I'm flattening the slope. That does not meet my objective, giving too many berms, because then I might as well make a gentler slope. So what have I done? I have put a T allowable of 30 and a T allowable of 40. This is normally not possible with geomembranes. This implies that I'm using a geogrid. Is there a problem you can't see? I hope the camera can catch it. So now let's look at the results. I started with a very ambitious slope. Well, let's look at the gentlest slope. I started with the gentlest slope of 4:1. Everything is stable. Height between berms 5, 7.5, 10. Beautiful factors of safety. Unimaginably high factors of safety. And I go to a slope of 2:1. I'm trying to get a slope which I normally can get in soils. Can you make an embankment of 2:1? 2 horizontal to 1 vertical is a slope with which you can make an embankment or no? Definitely. So let's see whether we can make this. There is a geotextile, a geogrid of 30 kilonewton per meter and 40. So 2:1, and I find 5 meters is too small. So the client was more interested in having a berm height between berms of 7.5. I'm going to look at the solution. My dry was 1.19. Why? Because the delta was 17. Because it was between geomembrane textured and geotextile. It was not between geomembrane and sand. Delta was 17. And 2:1, 1.19, below 1, below 1, below 1. So fail ho gaya slope. Even if you take T to 40, nothing exciting happens. 1.19 goes to 1.73, good. 0.93 goes to 1.31, good, because we wanted 1.3. 0.81 goes to 1.05, okay. But dare say if there is rain and earthquake, it falls below 1, and that's not acceptable. So 2 didn't work, so we tried 2.5. Let's make the slope flatter. Does it work? With 30 kilonewton per meter, 1.48, almost 1.5, okay. But seepage is still below 1.3, right? And earthquake it doesn't work, and earthquake plus seepage doesn't work. But if I take 40 kilonewton per meter, 2.16 is more than 1.5, 1.63 is more than 1.3, 1.21 is more than 1.1, and 1.02 is more than 1. This is the rarest of the rare. This is not likely to occur. Some courts may not even ask you to do it. But we were doing this for Bombay. And Bombay, when the monsoon comes, does it come? How do we know? Because every year we see flooding in Bombay and amount of water. So we just said we'll try this. So with 40 kilonewton per meter, now the only thing is, can you hold 40 kilonewton per meter at the top? How many 40 kilonewtons, just to convert it into tons, how many tons is this? Four ton. It's like a truck full of 4 tons of waste, and every meter has to hold that. So will a soil of 1 meter width hold a truck from falling down? We'll have to find that out. So while theoretically, if you give it attention, you have to see whether the anchor trench will hold or not. I can give you a product which will give you 40 kilonewton per meter. I can give you a design which works, but the design will only work if the 40 kilonewton per meter can be held where? At the top or at every berm? Because the solution is for 7.5 meters. If you are going to say at the top, suppose there are 4 berms of 7.5, take 30 meters, multiply this by 4, and then you have to do 4 times, because every segment has an unbalanced tension. So this has to be done at every berm. And how much width do you have in a berm? 1.5 meters. So a little complicated, but anyways, theoretically there's an answer. We were hoping that with 30 kilonewton per meter, this would become stable, 7.5. Dry was fine, seepage was fine, earthquake was fine, but this was still 0.93. So what it told us was that even with all this, if I want to use a T equal to 30 kilonewton per meter, I have to use a slope of 3.5:1. Okay? With everything we have done, might as well use 4:1 and be happy. I'm saying now, putting 30 kilonewton per meter, reducing it with a geocomposite, nothing great happened. Because 4:1, the delta would be very low, but beta would be much lower. So let me now go back and see, we have to, there are 1, 2 and 3 geosynthetics which are coming in rolls, right? And all of them have to be anchored at the top. So what happens when I look at the construction drawing at a berm? It just goes crazy. It's not so easy to construct the anchor trench and put 1, 2, 3, 4 materials inside it. And then you have to wrap it around because you're not getting enough capacity. So the geomembrane, then the geotextile, and the geocomposite, and the geogrid, everything has to be, it comes up the slope, it has to be put in a trench, it has to be wrapped around, and you have to make a berm at the top, and you have to have a drain, and so this is complicated. If I was to make it 4:1, maybe 4.5, 4.25:1, I may not need any anchorages. So this whole thing is, sometimes the solution are complicated. Let me take another example with you. So far we have been discussing about interfaces. Let me now focus on another aspect. I said excavated slope I have to analyze, waste slope I have to analyze, and I have to analyze the interfaces. I have done the interfaces. This is a landfill which is under construction in West in India, and it was originally designed for a height of 14 meters. And the outer slope is 4:1, very, very gentle. The owner said, I want to make this landfill to 31 or 32 meters high. I want to store more waste. So this was the original landfill. This is the 31 meter high landfill. He asked us to check the stability of this, not the interfaces. Interfaces we had checked, right? This is what the landfill looked like in plan. And this is the top of the landfill and the base profile, and this is the little flat ground at the top. It's like a conical mound going up, okay? And do see that this is about 300 meters, and if you are coming 4:1, 30 meters, 120 meters will go here, 4:1, another 100, 200 meters will go there, all that will be left at the top is 40, 50 meters. It was an above ground landfill, not below, above ground, that's the leachate collection well. These are the multiple double composite layer, that's the cover system. You can see the geomembranes and everything. We are not discussing this stability. We are discussing this stability, stability of the mass. Objective, check the stability of the waste mass for the proposed height of 32 meters. Check the stability of the cover system at various interfaces, which we will not discuss. Check the stability along the base liner. Base liner. Conditions of analysis. Okay, when you want to do the waste mass, what conditions would you adopt? For an embankment or for a dam, what are the conditions of analysis? You normally do 3 conditions for a dam. You do 2 conditions for an embankment. For a dam, what are the 3 conditions of analysis? End of construction, steady state seepage, and rapid drawdown. End of construction means the embankment after compaction as it has come up. Steady seepage means the reservoir has become full and there's a phreatic line which has developed, and rapid drawdown means this falls rapidly to a lower level. That's what we do for an embankment. What do we do for a landfill? We are talking of failure through the waste mass. Well, a few similar conditions, but first is the dry case. First is the dry case. Second is with leachate head. See, unlike an embankment which doesn't have a liner at the bottom, if any rain comes through, it will go down, right? Here we have made a liner and we have got a leachate collection system, so there should normally be no leachate. Maximum head should be 30 centimeters corresponding to the thickness of the leachate collection layer. But what do we have here? We have a liner. Suppose the leachate collection system is clogged. Suppose it becomes clogged. Then the leachate will rise inside the landfill. So when we are saying we have to do with leachate head, it means leachate to some level. When you do a road embankment, you also do an analysis with rain. And rain is simulated by a pore pressure parameter RU. So you can also have that means it is simulating rain or moist case, not fully saturated, but you have wet waste, therefore you are having pore pressure development as the layers come on top of the other. Then of course with earthquake, so these are some of the cases which one can analyze for the failure through the mass. I am talking of these failures. And one more failure that I am talking about is, I told you, because we have a base liner which may have a geomembrane, that may be an interface which is very weak. In all the landfills that we have designed, we have kept the base liner smooth because we said there is no slope, right? But we did not realize that you can have failure like this. So our delta is very low for the base liner, delta is high for the side slope liner, and see what happened in this case study. So we did stability of waste mass in temporary and permanent waste slopes. Permanent waste slopes of 4:1, not a problem. The temporary waste slope is when the waste is being filled up, they tend to have steeper slopes. So they are steeper than 4:1, so we are looking at 3:1. We did static slope stability of dry mass, static slope stability analysis of waste mass with 2-meter leachate level, signifying clogging of leachate collection layer. We did static slope stability of wet mass, pore pressure ratio of 0.2 RU, 2 cases without and with leachate level, that means with clogging and without clogging, and finally slope stability analysis of dry and wet waste mass under earthquake by the pseudostatic method. So these were the conditions which we analyzed, and these were the properties that we used: unit weight, cohesion, angle of shear, and these were the interface values that we used. Important thing for you to note is that at the base also we have a liner and smooth geomembrane clay liner interface 10 degrees. Okay? Textured geomembrane clay liner is on the slopes 24 degrees. That is not what we were really analyzing here. And we use the same factors of safety which we have discussed in our earlier class, and here are my results. This temporary waste slope, it is assumed that before the cover is put, the temporary slope has reached the top. This is 31 meters high. Dry waste, no leachate head, factor of safety is 1.683. I don't know, you can't read it here, but it's here. 2-meter leachate head, 1.503, all very stable. Wet waste, RU is equal to 0.2, 2-meter leachate head, 1.201. And dry waste, 2-meter leachate head, pseudostatic with earthquake, 1.115. So just look at the shapes of the failure surfaces. When the leachate head comes, then the failure surface tends to pass through the leachate. When there is no leachate head, it's a general large failure surface, but here the leachate head, this blue line shows the leachate head, and therefore it's passing through this. And if I look at the final critical factors of safety, this is a temporary slope, so the acceptable factor of safety is 1.3. Here we got 1.683, 1.5, more than 1.2, and like this we got the factors of safety with RU fine, with RU and leachate head fine, and so on, and so included pseudostatic where this was better than the acceptable factor of safety. So the temporary slope with circular failure surface was fine, no issues. We just said let's now put the delta 10 degrees here and now convert the problem into a 2-wedge problem, right? And this is smooth geomembrane, 3:1, dry waste, no leachate head, 1.359. Since it is temporary slope, 1.3 is acceptable. But dry waste, no leachate head, pseudostatic method falls to less than 1. So that is the problem, that because we had a 10 degrees here, the slope is not stable. If the waste is full and an earthquake comes, then it can just slip off the base geomembrane. And all these red marks came out of the 2-wedge analysis. So while the circular slip surface was all clear, the interface was pulling it towards itself because it is the softer interface. We just checked what if we had used textured, what we were using at the side. And the moment you use textured, factor of safety 1.9, 1.411. Everything becomes stable. In fact, it even becomes stable for 1:2.5:1. So luckily, you know, this is a landfill which is going like that, forward. And we are in our second year of construction at the moment. We still have another 15 years to come. So we have replaced all the geomembranes. For the future, the base will also be textured, because textured base gives you good values. Now I thought that one of you will ask me this question, that how did you use 24 degrees for textured with clay, because I have given you the table, it is typically 10 to 15 degrees. Well, this stability analysis was done by an overseas consultant, so they have given us this value. So we told the owner that we think it should be about 18 degrees. But if your consultant is underwriting this, it's fine. When you make the geomembrane very rough, it will become a clay to clay failure, right? And what is the phi dash of clay? Less than 25 degrees, 22, 23, 24. So the thought in this design is that it is a clay to clay failure in a textured geomembrane. Okay? So this has to be actually determined from the lab tests. It is very, very critical. So the conclusion is that even if circular stability analysis gives you fine, please go to the weakest interface. It's just like going in the zone dam. You have to do a two-wedge method along the core. Similarly here also, please do a two-wedge method along the base. And now let's come to the final thing about anchorage. How do we anchor the geomembrane at the top or at the berm? Both your geomembrane and a reinforcing geograde, if you are using the T, you have to anchor them to the top, right? And the simple thing is, if you have a lot of horizontal length available to you, right? Here is your geomembrane coming up. You take it horizontally. There is cover soil at top. You take it horizontally. And you keep on taking it till you get the capacity. After all, what is this capacity? Q tan delta, right? So this is called horizontal anchorage. At the top of a landfill, you may take a geomembrane very far horizontally, a few meters, to hold the soil, to hold the geomembrane even if the soil wants to slip. Then the T will be generated. However, this long length may not be available to you. फिर आप क्या करोगे? If you are on a berm, what will you do? You have this problem. This is your berm. Your geomembrane is coming. What will you do? You want 5 meters, you don't have 5 meters. So then the tendency is to put this in a trench, dig a trench here, and that's called an anchor trench. So anchorage can be by just run out, or anchorage can be through a trench. And here are some configurations of trenches. Run out, just going down, L, narrow trench. Sometimes you may not be able to excavate vertically. Then V shape, half V, double trench, U shape. So these are the kind of anchorages which you can try. It's not very simple to bend these thick geomembranes. Do remember that they are not like your thin things which can be, like cloth that they can be bent, but they do bend and you can do the anchorage. Next, therefore, the question is, what about the capacity? So there are many theories. There's Sharma and Lewis, and there's a Koerner's theory, and there's a Kuan's theory, and Willard and Cherrier's theory. You can take one of them and design them. The simplest is Sharma and Lewis. But let me see how you would like to solve this problem. If I have this is simple, as I said, there is normal stress here, and therefore there is a reaction of the ground, and therefore there is a resistance. Agreed? So actually it should be, if this is Q, this is L, and this is Q, then QL tan delta top plus QL tan delta below. Because as you will pull this, there will be friction at the top and friction at the bottom. But you know, when your cover goes up, it is possible that when you pull the geomembrane, the cover will also come out, because it's not very thick, it's not held in, restrained in position. You have like this, so maybe this will move out along with the geomembrane. You put some soil on a geomembrane and try and pull it, the top soil can come with it. So therefore, one tends to neglect this. Though then you should take this shear strength into account. Though you should then take this shear strength into account, but that is not taken into account in design. It's a conservative design. The more important question is, if you have a geomembrane like this, then what is the additional resistance which comes? Quite clearly, there will be a resistance here which is equal to this. How will this give you any resistance? Well, there are four theories. One of the theories is that it is this plus the, if it behaves like a rigid wall, what will happen? PP minus PA. Agreed? This QL tan delta below plus PP minus PA. This is assuming that the whole thing is rigid. But if you have assumed that there are frictionless pulleys here, just assume that there are frictionless pulleys, then what is it? This and, again somebody may not be able to see it, if there are frictionless pulleys, then the mechanism is different. You are pulling it, you will get friction here, the top soil is moving out with it, there is a frictionless pulley here, this will want to come up, so it will be the P tan delta. There will be friction on both sides of the geomembranes. So these are two different theories, one by Koerner and one by Sharma and Lewis. Okay? And if I was to try and summarize it here, this is the Koerner's theory. Please understand what does Koerner do. I just want your attention. The formula is very simple. This is T. Koerner breaks up T into T cos beta and T sin beta. There is a horizontal pull T cos beta, and he will do the stability by taking equilibrium of horizontal forces. T cos beta will be equal to QL tan delta, but there is also a T sin beta that adds to the reaction. It gives you a triangular reaction here, so it becomes T sin beta tan delta is an additional, because this T sin beta is bringing this down. So please see, T cos beta is equal to Q tan delta, that is the resistance along this force, plus T sin beta tan delta, because this is pushing down T sin beta, it is T sin, assume this T sin beta is acting here additionally. So T sin beta tan delta, that's his equation. And when there is a trench, T cos beta minus T sin, this equation is the same, plus PP minus PA. Passive pressure will develop here and active pressure will develop here. This is Koerner's approach. You will have this on Moodle, so you can look at it more carefully. But if you have any questions, I can answer them. But unless you do model tests, it will not be refined. What does Sharma and Lewis do? Sharma and Lewis say there is a frictionless pulley here and there are two frictionless pulleys here. So they don't resolve T. This is T, it's like a rope, there is a frictionless pulley, so here the T is horizontal. So T is equal to QL tan delta, topsoil is moving, and here is another pulley, so that T is here also. So T is equal to QL tan delta plus P horizontal tan delta on the trench side and P horizontal tan delta on the right side. Now the P horizontal can be active, passive or at rest. Mostly in the case of Sharma and Lewis, P horizontal is taken as at rest, K naught condition. Okay, is taken as K naught, because this is dug up and this is backfilled. Once you backfill it, you get the K naught condition for the purpose of analysis. So these two approaches give you very different results, but this is the way you check whether you can give the anchorage capacity that you need or not. So your T must be available from here, and you can put a factor of safety on it if you want to be very, very sure. Let me go back. Here it is, T becomes T cos beta. T cos beta is equal to QL tan delta plus T sin beta tan delta, because T sin beta is the downward component, and here it becomes T cos beta is equal to QL tan delta plus T sin beta plus PP, that is the total pressure minus the active earth pressure. Here it is T is equal to QL tan delta and T equal to QL tan delta plus pH plus J. This is the more conservative approach. It will give you larger lengths than Koerner's approach. This is the most conservative approach. So with this, we end our discussion on slope stability, and in a sense, philosophically, if you are not relying on T, then it's a passive system, right? There is no tension in the elements. So if you use 4.5:1 or 4:1, you may not have an issue of requirement of, but you want to go to 2.5:1 with the 40 kilonewton per meter I showed you. You can use berm heights of 7 or 6 meters, but you will need to hold these in position, and design of anchor trenches is a current area of research. Not anchored, anything, anchor weights, anchors, run out lengths, wrap it around a pipe, all kinds of work going on in this area. So thank you, and we will continue in the next class.